Hello everyone and welcome. Today we're going to be talking about reactant and product mixtures in the context of combustion chemistry. Okay, to start off we're going to be talking about stoichiometric mixtures. So we say a stoichiometric quantity of an oxidizer is the amount needed to completely burn a quantity of fuel. In the event where we have more oxidizer than we have fuel, we say this mixture is lean, or fuel lean. And in the event that we have more fuel than oxidizer, we say that it is fuel rich, or just rich. Now, the stoichiometric oxidizer, or air, fuel ratio is determined by writing a simple atom balance, assuming that the fuel reacts to form a set of ideal products. For a hydrogen given fuel, so if we use this, hydrocarbon given fuel, burning with air, complete combustion corresponds to all the fuel carbon oxidizing to form CO2 and all of the fuel hydrogen oxidizing to form H2O. So we can kind of express this relation in the following form. Again, considering that we have a hydrocarbon, we would write this equation as follows. We have O2 plus 3.76 N2 Now you may be wondering, why do we have this 3.76 here? This is to kind of simplify the composition of air. So we assume that we have 21% O2 in air, and we assume we have 79% N2 in air. So essentially, if we were to correspond this to moles, this corresponds to 1 mole of O2 for every 3.76 moles of N2. So that's why you'll always see this when we're talking about air. So assuming that we are combusting with air, that's what you'll see. Now, if we were to actually balance this with, say, a real sort of equation here, you might be wondering, well, what is A? Right? If we were to have a real hydrocarbon, what would we do? If this is a real equation, what would A be? A actually takes the form of A equals X plus Y over 4. So we'll be able to solve for A, assuming that we knew what our fuel was, assuming we knew what our hydrocarbon was we were working with. So if we actually go and choose a hydrocarbon, let's use CH4 as an example. We'll leave A as it is for now, and we'll fill it in just a minute. Now, we see that our C is technically 1 for this hydrocarbon. We don't write the 1, obviously, but it's technically 1. So we would say that we have 1 in front of the CO2, but again, we don't write that because it's just 1. And then our Y value is 4. 4 divided by 2 is 2, so we have 2H2O. And then, I think I made a mistake over here, it's 3.76A for the N2, plus 3.76, and then we have A for N2. Now we can go ahead and calculate A. A is equal to X plus Y over 4. So we have 1 plus 4 over 4. So our A value is 2. So if we go ahead and incorporate this, we get the following stoichiometric equation. And you can multiply the A value by 3.76. I'm just going to leave it as is for now. But that would be your stoichiometric equation, and I'll put a little box around it. Okay. Now that we've written out our stoichiometric equation, we're going to introduce the stoichiometric air-fuel ratio. Okay, so stoichio, oops, made a typo. Okay, so we can express this as A over F, and then we put a little red stoic at the bottom there, is equal to M air over M fuel. Again, for our stoichiometric equation, over 4.76 A over 1 MW air over MW fuel. Now, what are the difference between these two portions of the equation? What's the difference between this and the difference between this? Well, it has to do with what M air and M fuel are and what MW air and MW fuel are. This represents the actual mass. So this is like the mass. Sorry, not the actual. Like this represents the stoichiometric mass of air. And then our stoichiometric mass of fuel. Whereas these are the molecular weights. The stoichiometric molecular weights of air and fuel, respectively. So that's what makes this a little bit different. This A value that you see here, that's the same A value we calculated in our equation, so that would be x plus y over 4. Okay. Okay, so now we are going to move on and talk about the equivalence ratio, which is denoted by the symbol phi. And the equivalence ratio is commonly used to indicate quantitatively whether a fuel oxidizer mixture is fuel rich, fuel lean, or stoichiometric. And we can write out this relation with an equation as follows. We say phi is equal to AF with the stoichiometric air-fuel ratio, and then we have AF with the actual fuel ratio. By this definition, we see that if our value of phi is greater than 1, this is a fuel-rich mixture. If our value of phi is less than 1, this is a fuel-lean mixture. And if our value of phi is equal to 1, then this is a perfectly stoichiometric mixture. Okay, in many combustion applications, the equivalence ratio is the single most important factor in determining a system's performance. Other parameters we frequently use to define relative stoichiometrics. Relative stoichiometry are the percent of stoichiometric air, which kind of relates to the equivalence ratio as follows. We say percent stoichiometric air, which is equal to 100% divided by equivalence ratio. And then you might also stumble across the percent excess air, which is equal to 1 minus phi over phi times 100%.